Hey everyone, I just wanted to make a video on transformations. This could be the third time I'm recording this thing because they keep making announcements to mess them up on the speaker here, but that's okay. Okay, so for transformations, first thing I want to point out is that we are transforming simple power functions, and that means the parent function of every single one of the functions that we're going to be looking at in this particular section is going to be in the form of f of x equals x to the power of n. And I want you to remember that n, right, is the degree of our power function. We give it n because, of course, we know that the power function can have lots of different degrees. You know, we could have degree 3 or degree 7 or, degree 10. We just want to have a number, or sorry, a variable to stand in for some number. So we have that as degree n, right? Letter n. Okay, so we know that the transform function is going to look like the form of g of x is equal to a times k times x minus d all to the power of n plus c. Note that the power of n is affecting everything inside of our square brackets, okay? And note that this does look a lot like stuff that we've learned about last year in grade 11. It actually is pretty much the same thing. The only difference being that this is, of course, applied to a power function. So because we learned about this a whole lot last year, I'm kind of expecting that most people remember how the different values of a, k, d, and c are going to affect the graph, right? You know, if a is positive, what does it do? If a is negative, what does it do? And so on. If you do need a refresher on that, though, what I'm going to do is I'm going to encourage you to take a look at page 14 in our workbook, because it does give you a bit of a summary on that. But I am going to assume, for the purposes of this video, that you do somewhat recall those things, okay? So the best way to go through these things, I think, would be to go through an example. So let's take a look at the following example. So what is the equation of the polynomial function resulting from y equals x to the power of 4 being vertically stretched by a factor of 2, reflected in the x-axis, horizontally stretched by a factor of 3, shifted up 4 units, and shifted left 1 unit? Okay, so we're going to try to come up with the equation for that. Okay, so whatever the equation is, we know, of course, it's going to start with y equals, so why don't we toss that in there for now? And the other thing I want to point out to you is that the parent function is a degree 4 power function. You can see that because this is the function that we are transforming, y equals x to the power 4. So it is a degree 4 power function. Okay, so if you take a look at our general formula for a transform function up top in green, we have g of x is equal to a times k times x minus d to the power of n plus c. We, of course, need that a value first, so we have to recall what is going to affect that a value in terms of the description. So remember that a is affected by vertical stretches and compressions, and is also affected by vertical reflections, which are reflections in the x-axis. In our description, you might be able to see that we are vertically stretching the function by a factor of 2. Now that would indicate to us that our a value would be 2, but you also have to notice that we have a reflection in the x-axis, and that means that our a value is going to be negative. So our a value is actually going to be negative 2. Okay, and we're going to open up that square bracket. Next thing we need to know is our k value, and remember that the k value is being affected by horizontal stretches and compressions, and also horizontal reflections in the y-axis, that is. Look at our description. You're going to notice that we are horizontally stretching by a factor of 3. So that means that our k value is going to be, well, hold on, before we actually say what it is, I want you to remember that the k value is kind of one of those weird scenarios where you're not going to be able to pull the value straight out of the description like that. It's kind of backwards. The k value is going to be the reciprocal of the value from its description. So if it's being horizontally stretched by a factor of 3, we are expecting our k value to be 1 over 3. So that's what we're going to put, 1 over 3. Okay, now we need to put x minus d. Well, we know that the d value decides how we shift to the left or the right. If you look at the end of the description, it says the function is shifted 1 unit to the left. And of course, we know that that's going to look like this when we put it in, x plus 1. Right, that's a shift of 1 unit to the left. Now we need the exponent n, and again, I'm going to direct you to our parent function, which is y equals x to the power of 4, and that's a degree 4 power function, so that means that we're going to have a degree 4 polynomial function after our transformation, so that's what we're going to put in next. And then the last thing, our plus c, remember that that's just shifting up or down. You're going to notice that we have a shift up 4 units, so our c value is going to be plus 4. Okay, so this is going to be the equation that we're going to be dealing with. The next question I have for you guys is, well, what is the domain and range of this function? So I'm going to open up a new page. We're going to talk about that. Okay, so I'm just rewriting our equation right here. This is the equation that we got. So we're stating the domain and range for this. What we're going to do to help us is we're going to remember some properties of our parent function. So remember that our parent function is y equals x to the power of 4. Now, we can sketch a graph of this pretty easily. We have an idea as to what this looks like, so that's what we're going to do first. And I want you to remember that y equals x to the power of 4, since it is an even degree power function, and since its degree is higher than 2, it's going to look like almost like a parabola, right? But there was one important difference. It almost flattens out close to the bottom, right? So what I'm going to do is I'm going to draw my x and y axis, and I'm just going to draw a somewhat horizontal line close to the origin here. And again, the reason why I'm drawing that line kind of horizontally is because we know it flattens out close to that place. So I'm going to kind of use that as the position for which it flattens out rather. So from here, it's going to branch off in either direction, right? And we're going to get something that looks like that, right? So again, it's a parabola pretty much, at least it looks like a parabola, with the main difference being that it flattens out towards the bottom. Okay, how about the domain and range for the parent function? Well, parent function is a kind of polynomial function, remember. And we learned that every single polynomial function has a domain of all real numbers, so we know that the parent function has a domain of all real numbers. How about the range? Well, it's like a parabola. Specifically, it's like a parabola that opens up. And that means that it's going to be all y values which are bigger than or equal to some number. And if you notice, it crosses at the origin, and that looks like where it's going to be its lowest point. So our range is going to be a set of y values which are elements of the real number system, such that y is greater than or equal to 0. Okay, so since we know that, why don't we use the domain and range for the parent function, and use the transformations in our equation to come up with the domain and range. So our domain, well, our transformed function is also going to be a polynomial function of some sort, so its domain is also going to be all real numbers, right? Just like every polynomial function. Now the range, well, we know it's going to be in the form of y is bigger than some number, or y is less than some number. Or I guess it's more like y is bigger than or equal to some number, or y is less than or equal to some number, and we have to figure out what that number is. Okay, let's see. For our range, the first thing that we need to know is whether it's going to be y is bigger than or equal to, or y is less than or equal to. And what's going to tell us that is that there, right? We have our negative sign for our a value. That tells us that this is going to be kind of like a parabola that opens down, and we know that those, of course, have a maximum value. And since it has a maximum value, we're going to have all of our y values be less than or equal to some number. Okay, so why don't we write that in? We're going to have y as an element of the real number system such that y is less than or equal to something. Okay, so what is that something? Well, if you take a look at our function again, right, we have a plus 4 at the end. And what that does is it shifts our function up 4 units. So if we didn't have that plus 4, right, all we would be doing that would kind of make a difference for the range is reflecting the parent function so that its end behavior goes, instead of from quadrant 2 to quadrant 1, it will turn into quadrant 3 to quadrant 4. And that means that our maximum value would still be at the origin. But since we're shifting up 4 units, it's no longer at the origin. It's going to be 4 units above that. So that means that all of our y values are going to be less than or equal to 4. Okay, cool. So now that we have the domain and range, there is one other thing I wanted to do with this, and that's sketch it. So this sketch is going to be a very rough sketch. It's going to give something that looks like the function, but it will not give us specific points. It won't be a very detailed sketch. If we want a detailed sketch of this function or a detailed graph of this function, a couple things that we could do. We could use a table of values, right? Just make a table of values for our transform function, plug in some x values and see what y values you get. That would be one way. Another way to do it, it's not quite as quick a way, but one way you could do it as well is to get some points on your parent function and then use the mapping rule or mapping notation to get some points on your transform function. That'd be another way to do it. But table of values would actually be pretty quick. We're not going to do either of those things. We're going to have a very rough sketch, right? And that's what all you need for most of these anyways. So here's what we're going to do. We're going to draw an x and y axis. First thing that we need to remember is that this, again, it looks like a parabola, so our transform function is going to look like a parabola of some kind. Now, usually when you're drawing a parabola, you draw the vertex first, and that's exactly what we're going to do. So the things that are going to contribute to what is kind of like our vertex here are shifts, right? Shifting to the left, shifting to the right, shifting up, shifting down. So remember that we did shift 1 unit to the left and 4 units up. And you can kind of see that from here, right? That's the shift of 1 unit to the left, and here that's 4 units up. So we're going to plot a point, right, that is kind of like our vertex. So let's see, 1 unit to the left, 4 units up, and we're going to plot a point there. Cool, so that's kind of like a vertex. So the next thing we need to remember is that this is a degree 4 power function, or polynomial function, I guess technically. It's a degree 4 polynomial function. And we know that those are kind of flattish around the bottom. So I'm going to kind of draw a little bit of a horizontal line to show that this has been flattened out. And we, of course, know that the function was reflected such that it now opens downwards. So we're going to have 2 arrows branching out from there and there. Okay? And this is a very rough sketch of our graph. So again, if we wanted a more detailed sketch of this graph, we could just make a table of values and come up with some points and plot those. No big deal. If we just want like a rough sketch, then we can plot our vertex, right, or our origin point, or whatever you want to call that, right? Consider any reflections and just kind of eyeball it a little bit, right? We won't get certain details of our function. Like we won't know exactly what the y-intercept is or exactly what the x-intercepts are, but we'll get an idea about what the function looks like in general. Okay, guys? So I hope this is useful to you. I hope it helps you with your homework. But we'll definitely take some time to take up the homework when you guys get back into class. Take care.